In 1977, NASA launched two spacecraft that were never expected to leave the solar system. They were designed to photograph Jupiter and Saturn, to get close enough to read their cloud formations, measure their magnetic fields, and map their moons. The planetary flybys would take roughly 4 years. After that, the mission would be over. The spacecraft would drift away into the darkness, their instruments silent, their cameras dark. That is not what happened. 48 years later, both spacecraft are still transmitting. Both are operating beyond the boundary of our solar system, in a region of space that no instrument had ever directly sampled before Voyager crossed into it. And what they have found out there, in the space between stars, is not what anyone predicted. The interstellar medium, the vast ocean of gas and magnetic fields that fills the galaxy beyond any star's influence, turns out to be far stranger and far more structured than the best models suggested. And at the same time, the James Webb Space Telescope has been doing something equally significant in the other direction, looking outward rather than in place, analyzing the atmospheres of planets orbiting other stars, and the results it is finding in 2025 and 2026 have been quietly rewriting the list of worlds where life might be possible. What NASA has actually found beyond our solar system is not a simple story. It is a collection of surprises that the agency has not always communicated clearly, and that deserve considerably more attention than they have received. Start at the edge. The heliosphere is the enormous bubble of charged particles and magnetic field that our sun creates around itself, extending far beyond the orbit of Pluto into space. For most of human history, everything humanity knew about the universe came from inside this bubble. The solar wind fills it, the sun's magnetic field shapes it, and everything beyond it was a theoretical unknown. Then Voyager 1 crossed the boundary in 2012, and Voyager 2 followed in 2018. They entered what scientists call the interstellar medium, and what they found there immediately began overturning the models. The boundary itself was not what anyone expected. Scientists had predicted a gradual transition zone, a fade from the sun's influence into the background of the galaxy. What both Voyagers found was sharper, more defined. A boundary that researchers described as behaving like a wall. The temperature at the heliopause, where the sun's solar wind meets the incoming interstellar medium, reached levels that genuinely surprised the teams analyzing the data. The solar wind, as it presses against the interstellar medium, does not simply slow and cool, it heats up dramatically. The particles in the outer heliosphere reach temperatures in the tens of thousands of degrees as they decelerate against the incoming galactic material. Scientists began calling this region the Wall of Fire, a phrase that captures something real about the physics. The sun does not simply end, it collides, continuously, with the rest of the galaxy. And that collision is energetic in ways that the models had significantly underestimated. The magnetic field findings were equally unexpected. Both Voyagers found that the magnetic field lines just beyond the heliopause are more ordered and more compressed than predicted. The interstellar magnetic field is pressing harder against the heliosphere than models suggested it should, warping the boundary's shape and creating a structure that researchers are still working to fully characterize. These are not minor calibration corrections, they represent fundamental surprises about the large-scale structure of the space immediately surrounding our solar system, a region of space that shapes the environment in which Earth exists and which, until Voyager crossed it, had never been directly sampled by any instrument. Then there is the hum. In 2021, scientists at Cornell University analyzed data from Voyager 1's plasma wave system, the instrument that detects oscillations in the charged particles of the interstellar medium, and found something that had never been detected before: a continuous, faint, persistent vibration in the plasma of interstellar space. Not a burst, not a pulse. A steady, narrow-frequency hum that Voyager 1 had been moving through for years without anyone initially recognizing it for what it was. The hum is produced by thermal oscillations in the very low-density plasma of interstellar space. Electrons and ions at temperatures of a few thousand degrees, jostling against each other in the near vacuum between stars. Its significance is not in the sound itself but in what it tells scientists about the structure of the interstellar medium. The density of the plasma is higher than the models predicted, and it varies in ways that suggest the interstellar medium is not uniform but has structure, turbulence, and features at scales that existing instruments can only barely resolve. As Voyager 1 travels further into interstellar space, the hum is changing, and those changes are encoding information about a region of the universe that no instrument has ever visited before. Every day that Voyager 1 continues to function adds a data point from a location no human object has ever occupied. The probe is now more than 24 billion kilometers from the sun. The radio signal carrying its data takes more than 22 hours to reach Earth at the speed of light. But beyond Voyager's direct insight of sampling, the more scientifically transformative findings of the last 18 months have come from the James Webb Space Telescope's systematic analysis of exoplanet atmospheres, and specifically from its ongoing investigation of the TRAPPIST-1 system. TRAPPIST-1 is a red dwarf star approximately 40 light-years from Earth, orbited by 7 Earth-sized rocky planets. 3 of these planets sit within the habitable zone, the range of distances where temperatures might allow liquid water on a planetary surface, No other star system currently known to science contains so many Earth-sized planets in the habitable zone. When Webb was launched, the TRAPPIST-1 system was at the top of every astrobiologist's priority list. The results have been arriving steadily through 2025 and into 2026, and they are more complicated than either optimists or pessimists predicted. TRAPPIST-1b, the innermost planet, was examined first. Webb's thermal emission measurements found no evidence of a significant atmosphere. The planet's dayside temperature was consistent with a bare rock absorbing and re-emitting stellar radiation without any atmospheric redistribution. This was the pessimistic outcome, and it was exactly what some researchers had predicted for planets so close to an active red dwarf star, whose flares and ultraviolet radiation strip atmospheric gases away over time. Then came TRAPPIST-1c, the second planet. It also showed no clear evidence of an atmosphere of any significant density. Then TRAPPIST-1d, the third planet, was examined by Webb in January of 2026. The results were published immediately. TRAPPIST-1d does not have an Earth-like atmosphere. The Webb data ruled that out cleanly. What it might have, the researchers noted carefully, is an extremely thin atmosphere, like Mars, or a thick cloud deck like Venus, that is blocking the detection of atmospheric signatures lower down. The planet is not definitively airless, but it is definitively not the twin of Earth that some had hoped. And then there is TRAPPIST-1e. This planet has received a different label from astronomers than its inner neighbors. It sits in the center of the habitable zone. Its size and mass are close to Earth's. Its orbit receives roughly the same energy from its star as Earth receives from the Sun, adjusted for the star's dimmer output. In September of 2025, James Webb observations produced a result that was described in published research as hints of an atmosphere around TRAPPIST-1e. Hints, specifically, that the planet has a secondary atmosphere, one that formed after the planet itself, rather than the primordial hydrogen-rich envelope that close-orbiting planets typically lose early in their history. A secondary atmosphere is more interesting than a primordial one. On Earth, the atmosphere we have now is a secondary atmosphere, produced by volcanic outgassing and eventually, by biological processes over billions of years. The researchers explicitly ruled out a hydrogen-rich primordial atmosphere for TRAPPIST-1e, pointing instead toward the possibility of something denser, something that could support liquid water on the surface. The observations are still ongoing. The result is a hint, not a confirmation, but the language used in the published research and in the Webb team's own descriptions of their findings is language that no one was applying to any exoplanet 2 years ago. Now go to a different system entirely, 120 light-years from Earth, a planet designated K218b. It is not a rocky planet like the TRAPPIST worlds. It is substantially larger, in the category scientists call a Hycean world, meaning it may be covered by a global ocean beneath a hydrogen-rich atmosphere. In 2023, Webb detected carbon dioxide and methane in K218b's atmosphere simultaneously, a combination that on Earth would be immediately interesting because methane in an oxygen-free hydrogen-rich atmosphere can be produced by life. In 2025, Webb's continued analysis of K218b maintained the methane detection and added further chemical characterization of the atmosphere. The researchers have been careful. Every molecule Webb has detected in K218b's atmosphere has an abiotic explanation, a way it could be produced by chemistry without any involvement of biology. The methane could be geological, the carbon dioxide is a common atmospheric constituent, but the combination of molecules, the specific ratios, and the ongoing effort to detect or rule out dimethyl sulfide, a compound that on Earth is produced almost exclusively by marine microorganisms, has kept K218b near the top of the scientific community's list of most interesting atmospheric targets. Webb's observation schedule for the rest of 2026 includes additional K218b transits specifically designed to improve the sensitivity of the dimethyl sulfide search. What all of this adds up to is a picture that is significantly more detailed, and in some ways more confusing, than what existed 2 years ago. The edge of our solar system turned out to contain a boundary sharper and more energetic than expected, compressed by interstellar magnetic fields, stronger than models predicted, humming with plasma oscillations that encode the structure of the galaxy's local environment. The nearest system of Earth-sized habitable zone planets has already yielded 3 planetary atmospheres that are either absent or too different from Earth's to sustain the kind of surface life we can currently detect, and 1 planet whose atmospheric hints are inconsistent with the pessimistic outcome, and a world 120 light-years away, in a completely different category from any planet in our solar system, is sitting at the edge of a biosignature detection that the instruments observing it are not yet sensitive enough to confirm or rule out. NASA has not found life beyond the solar system. It has not found a confirmed biosignature, but it has found a collection of results that has moved the question from where should we look to what exactly are we seeing here. And that transition is the most significant thing that has happened in the search for life beyond Earth in a generation.